have Professor Chen-Ning here with us today. Professor Yang received his Bachelor of Science and Master of Science degree from Southwest Associated University in China during the wartime. And in 1945, he went to the United States and got his PhD from University of Chicago in 1948. He spent another year in University of Chicago, then went to Institute for Advanced Study in Princeton and became a full professor in 1955. In 1966, he moved to State University of New York in Stony Brook and became Albert Einstein Professor of Physics and the founding director of the Institute for Theoretical Physics. And after his retirement, the institute was renamed C.N. Yang Institute for Theoretical Physics to honor his contribution to physics. Professor Yang made a great contribution to the advancement of our knowledge in physics and received many awards and honors because of his contribution, including the Nobel Prize in 1958. Among his work, the Yang-Mills gauge theory is the foundation of the Standard Model, and the Yang-Baxter equation opened up a new direction, okay, to the integrable model. And of course, his work with TDD on parity variation, okay, is a groundbreaking work. Okay, so we are really very lucky to have him this afternoon to give us a seminar, to give us a talk on conceptual origins of Maxwell equation and of gauge theory of interaction. So without further ado, let's welcome Professor Yang.
Said to me, I now really know I'm very old, because when I go to a conference, I would always be the oldest participant. Not only that, the next oldest participant is always 10 years younger than I. So I think probably the same applies to my feeling this afternoon at the Taiwan Dashi. I'm going to report to you this afternoon an article which has already been published in the Physics Today with the title Conceptual Origins of Maxwell Equations and of Gauge Theory of Interactions. It is usually said that Coulomb, Gauss, Ampere, and Faraday discovered 4 laws experimentally, and Maxwell wrote them into equations by adding. That is not entirely wrong, but it obscures the subtle interplay between geometrical and physical intuition that were essential in the creation of field theory. First, 19th century. The first big step in the study of electricity was the invention in 1800 by Volta of the voltaic pile, a simple device of zinc and copper plates dipped in seawater brine. before that, one cannot make any systematic study of electricity. After that, on a very, very small scale, but planned experiments were carried out. Then in 1820, Ørsted, a Dane, discovered that an electric current would always cause magnetic needles in the neighborhood to move. Ørsted's experiment electrified the whole of Europe, leading to such devices as the solenoid and to the exact mathematical laws of Ampere. Ampere was learned in mathematics. He worked out in 1827 the exact magnetic forces in the neighborhood of a current as action at a distance. Faraday was also greatly excited by Ørsted's discovery, but he lacked Ampere's mathematical training. In a letter Faraday wrote to Ampere, we read the following. I'm fortunate in a want to mathematical knowledge and the power of entering with facility any abstract reasoning. I'm obliged to feel my way by facts placed closely together. Without mathematical training and rejecting Ampere's action at a distance, Faraday used his geometric intuition to feel his way in understanding his experiments. In 1831, he began to compile his experimental researches, recorded eventually 23 years of research. It is noteworthy that there was not a single formula in this whole monumental compilation. This is an early edition. Hello? This is an early edition of the 3 volumes of Faraday's work. By the way, I was very pleased and impressed when I found that the Tsinghua University Library in Beijing had kept a copy of such a 19th century publication, indicating that the librarian or the curator of the library in Tsinghua in the early days was very knowledgeable. Then in 1831, Faraday discovered electric induction. This is a photograph from Faraday's diary of 1831 in October. It shows a solenoid with a coil attached to a galvanometer. He found that if you move the bar magnet in and out of the solenoid, one would generate electricity in the solenoid. Faraday discovered how to convert kinetic energy to electric energy, thereby how to make electric generators. That, of course, is one of the essential steps that made the 20th century possible. This was, of course, very, very important. But perhaps more important was his vague geometrical conception of what he called the electrotonic state. He did not define what this state was. In various parts of his experimental researches, you read about his names for this electrotonic state. Sometimes it's called a state of tension, or a state of vibration, or perhaps some other state analogous to the electric current to which the magnetic forces are so intimately related. This concept first appeared early in section 60, volume 1 of experimental researches, but without any precise definition. When reached in section 66, all matters take on the peculiar state. In another section, the state appears to be instantly assumed. Another section is called the state of tension. Faraday seemed to be impressed and perplexed by two facts. First, that the magnet must be moved to produce induction. A magnet which stays inside the solenoid without moving does not produce electricity. Second, that induction often produces effects perpendicular to the cause. The motion of the solenoid is horizontal, but the current is in the solenoid is perpendicular to it. Faraday was feeling his way in trying to penetrate electromagnetism. Today, reading his experimental researches, we have to feel our way in trying to penetrate his geometric intuition. And of course, that was also the case with Maxwell. When Maxwell started to study Faraday's works, he had to feel his way. Like today, we have to feel our way to try to understand what this geometric intuition of Faraday was really about. Faraday seemed to have two basic geometrical intuitions. First, magnetic lines of force, and second, the electrotonic state. The first was easily experimentally seen through sprinkling iron filings in the field. It is now called H, the magnetic field. The latter, the electrotonic state, remained Faraday's elusive geometrical intuition when he finally ceased his compilation of experimental researches in 1854. He was 63 years old. That same year, Maxwell graduated from Cambridge University. He was 23 years old. In his own words, he wished to attack electricity. Amazingly, 2 years later, he was able to publish the first of his three great papers which founded the electromagnetic theory as a field theory. Maxwell has learned from reading Thomson's mathematical papers the usefulness of an equation which in today's vector form is written as H equal to curl of A. Of course, in Maxwell's time, there was no vector notation, so he wrote it out as three equations, as Thomson did before him. Studying carefully Faraday's voluminous experimental researches, Maxwell finally realized that the electrotonic intensity of Faraday is equal to the vector potential A, defined by the equation H equal to curl of A. He realized that what Faraday had described in so many words was the equation E equal to minus time derivative of A. If you take this equation and take the curl of both sides, we get curl of E equal to minus H dot. This last equation is Faraday's law in differential form. Faraday himself had stated it in words which translates into this formula, which is well known today to all students of electricity and magnetism. So today we write this equation or the equation on the previous slide as Faraday's law. But actually, the one who really was able to write down Faraday's law was Maxwell. Comment. Maxwell used Stokes' theorem in his work extensively, which had not yet appeared in the literature. It had first appeared in the 1854 Smith Prize exam, which Maxwell had taken as a student. To prove Stokes' theorem was question number 8 in that year's Smith Prize examination. Thus, Maxwell knew the theorem, and he used it extensively in his papers. Stokes' theorem, of course, today in its generalized form is one of the cornerstones of modern differential geometry. Maxwell was well aware of the importance of his paper 1, of his identification of the vector potential with the electrotonic state of Faraday. To avoid possible controversy with Thomson about the origin of equation H equal to curve A, Maxwell wrote explicitly in his paper that with respect to the history of the present theory, I may state that the recognition of certain mathematical functions as expressing the electrotonic state of Faraday and the use of them in determining electrodynamic potentials and electromotive forces is, as far as I'm aware, original. That's, of course, a correct statement. But then he added, the distinct conception of the possibility of the mathematical expressions arose in my mind from the perusal of Professor William Thomson's papers. So, in this paragraph, you see very clearly two things. First, he was very proud of his discovery. Second, he was aware of the fact that he has extensively used Thomson's idea, and he was afraid that Thomson might take offense. 5 years after paper 1, he started to publish paper 2 in 4 parts, parts 1, 2, 3, 4, from the year 1861 to the year 1862. The displacement current first appeared in part 3 of this paper 2. It appears in proposition 14, which reads, to correct equation 9 of part 1 of electric currents to the effect due to the elasticity of the medium. That is to say, he added the displacement current to what had earlier been taken as Ampere's law. Maxwell arrived at this correction, according to his paper, through the study of a network of vortices. There are quite a number of diagrams of vortices in this paper too, of which the most interesting one, I think, is this particular one. You observe that what he was thinking of are a network of complicated vortices. Each of the small circle is a vortex, and then each of the hexagon is a larger vortex. And he had arrows showing the motion of the medium because of the collection of these vortices. By the way, and this has not been commented in the literature before, I noticed that there must be a mistake in this in his diagram, because if you look at the second row from the bottom of the hexagons, if you look at them carefully, you will find that they were not, the arrows were not in the right direction. After examining this carefully, I decided that this must be a typographical mistake of the draftsman of Maxwell. Maxwell took this model seriously and devoted 11 pages to arrive at the correction. I made several attempts to understand these 11 pages, but failed. With the correction, Maxwell happily arrived at the momentous conclusion. We can scarcely avoid the inference that light consists in the transverse undulations of the same media, which is the cause of electric and magnetic phenomena. That is to say, light is equal to electromagnetic waves. This is really a momentous discovery of great importance for mankind. Maxwell was a religious person. I wonder, after this momentous discovery, did he, in his prayers, ask for God's forgiveness for revealing one of his greatest secrets? Because of the importance of this discovery, I made several attempts, as I told you before, of how he arrived at the displacement current, thereby the whole 4 equations for electromagnetism. But as I said, I had failed. There have been books and books written about the discovery of the displacement current. None of them explained the procedure by which Maxwell arrived at displacement current. The word displacement did not appear in paper 2. It did not appear in paper 1. It first appeared in paper 2. And once it appeared in paper 2, it became a central idea. So the discovery of the displacement current evidently is a great turning point. And I think this is one of the great puzzles of science history about how precisely he had arrived at the displacement current. Did he really utilize his network of vortices, or did he merely extracted some ideas from the network of vortices and using the abstraction to write down the displacement current? I don't know the answer to these questions, but I think it is a first-rate historical question worthy of further study. Paper 3 was published in 1865. It had the title, A Dynamical Theory of the Electromagnetic Field. In it, we find the formula for energy density, which we teach to our students today, 1/4 pi times E squared plus H squared. In section 74, we read a very clear exposition of the basic philosophy of field theory. In speaking of the energy of the field, however, I wish to be understood literally. All energy is the same as mechanical energy, whether it exists in the form of motion or in that of elasticity or in any other form. He was referring to the first law of thermodynamics, which was already established at the time. The energy in electromagnetic phenomena is mechanical energy. The only question is, where does it reside? On the old theories, it resides in the electrified bodies, conducting circuits, and magnets, in the form of an unknown quality called potential energy, or the power of producing certain effects at a distance. In our theory, it resides in the electromagnetic field, in the space surrounding the electrified and magnetic bodies, as well as in those bodies themselves, and is in two different forms, which may be described without hypothesis as magnetic polarization and electric polarization, or, according to a very probable hypothesis, as the motion and the strain of one and the same medium. That was historically the first clear formulation of the fundamental principle of field theory. But Maxwell still believed there had to be an ethereal medium. Why? Because before Maxwell, waves always produce in some medium. How can there be waves in electromagnetism without any medium? So therefore, it is natural for Maxwell to assume that there is a certain medium which is called ethereal medium. My comment. Throughout his lifetime, Maxwell always wrote the equations with the vector potential A playing a key role. After his death, Heaviside and Hertz gleefully eliminated the vector potential A. But in the 20th century, with quantum mechanics, we now know that A has physical meaning. It cannot be eliminated. For example, in the Aharonov bomb experiment. '20th century. Thomson and Maxwell had both discussed what we now call the gauge freedom in the equation H equal to curl of A, because this equation, starting from H, does not define A uniquely. We all know you can add a gradient function to A, and that does not change this equation. It was in the 20th century, with the development of quantum mechanics, that this freedom acquired additional meaning in physics and mathematics, as we shall discuss below. The first important development in the 20th century in physics understanding of interactions was Einstein's 1905 Special Relativity, according to which there is no ethereal medium at all. The electromagnetic field itself is the medium. The next important development was the 1930 to 1932 discovery of the particle, which led to Dirac's sea of negative energy particles, in other words, to QED. QED was very successful already in the 1930s in low-order calculations, but was